So Uzy is known for numerous contributions to physics. He started as an experimental physicist doing nuclear physics, then he slightly converted into mathematical physics. And actually, I think that nowadays he is best known for his contributions to archaeology. He told us yesterday or 2 days ago that he had more citations in archaeology than in physics. And today he will speak about the distribution of delay times through graphs.
Thank you very much. And my biggest contribution to Polish science is to have him for 2 months in the Rehovot, and to have Tomek, who is not yet awakened, for another 1 month. And that was a great pleasure. So thank you very much for inviting me. I'm sorry about all this business. It was complicated, but never mind. The first time I gave this lecture was in England. And there you have to prove that what you do in mathematics is relevant for society. Now you know that in England the trains are very much delayed. And somebody took the trouble to make a lot of statistics and to find the frequency or the number of times that a train is delayed by 10 minutes, 20 minutes, 60 minutes. And I think that he was cheating at this point, because I think it goes this way and it continues. You can have a delay of 24 hours also. At any rate, then there was a theoretician who wrote this formula for it, and it fits the data wonderfully well. Now, when I told this to the audience in Queen Mary College, one of the gentlemen raised up his hand and he said, "Mr. Beckel is me." So the second author is him. I hope nobody of you is busy with such things. So this is what I'll talk about, and these are the delay times, but not about trains, but about other things. Now this work was done in, several people were helping me. The most important is Uzy Smilansky, he's my son, and I will tell what he taught me. And the mathematics of this is actually in this archive. I wrote a paper which is just now appeared in the Journal of Physics A, explaining the entire setup, the general setup. And there is something which I will come up at the end, which is based on the work which I did with Holger Schanz. So, what is the delay time? A delay time is when you have, think of it as a scattering problem. Think about, the best thing to think about is a pinball game. You throw from the same point many balls, and then they scatter around, and each of them takes a different path. And when you make many of them, you can measure what was the length of the path distribution for a particle to go from one point to the other point. And always it's the same, starting at the same point and ending. Suppose that you only look at ending at one point. So you have a distribution of time delays. And the delay time is the delay because you started at one point. If it were going straight, it will be the 0 time, and then you measure relative to this 0 time. This is a simple concept in classical physics. However, you can ask the question, what happens if you have waves or quantum mechanics? There are 2 problems. First of all, there is Heisenberg principle, which tells you that you cannot measure at a given energy a distribution of times. You either have a time, you measure time, either you have time or you have energy. So you have to have a theory which includes this automatically into the game. And then you don't add probabilities, you add amplitudes, and only then sum and square. And that means that you have superposition, interferences, and new phenomena occurs. The most outstanding is, of course, Anderson localization. That changes the picture completely, and I will speak about Anderson localization at the very end. So, my purpose is to propose a quantum mechanical theory for the time delay distribution, show you that it meets the correspondence principle. It is consistent with the correspondence, so that if you go to the semi-classical limit, you regain the classical dynamics. And I would like to make also a small warning. If you do by Google, you write delay time distribution, you always look at the distribution which is called the time delay, the Wigner time delay. This is Wigner, by the way, on a Hungarian stamp. And he introduced this concept T of E as a quantum mechanical delay time, but it cannot be correct because T cannot be a function of E. It's against the correspondence principle. And indeed, Wigner knew quantum mechanics quite well, and he was calling it the mean delay time. It is an average of a distribution. And when you look at in the literature now, then they call it mean delay time, but it is a mean not with respect to the distribution of times, but with respect to distribution of systems. You have a random ensemble of systems, you average over them, and you get the mean delay time. And that is where it is connected to random matrix theory and all this nonsense, and therefore you have a huge amount of literature about something which is called the same thing, but it means differently. It means that it is a mean with respect to the system and to the ensemble, and not with respect to the distribution of times. As a matter of fact, this concept was introduced in the past. Lubavitch introduced it when he was studying the distribution of resonances in nuclear physics. Blimel and myself introduced it 5 years later without knowing about Lubavitch when we studied chaotic scattering. But what we and he studied were actually this object, which is the autocorrelation function of the scattering matrix. And then we realized that if you take the Fourier transform, you get something which depends on time. And that is, you can prove, the time delay distribution. I shall show all these things by a simple system, which is graphs. And what I would like to do is, okay, I would like also to mention for those of you who are physicists that time delay or the measurement of time was not possible in the past because you did not have sharp pulses in time. You didn't have sharp pulses. And if you don't have sharp pulse, you don't know what you put in, and then you don't know what to put out. As a matter of fact, what you had were sharp energies. You have monochromatic beams. And when you have monochromatic beams, you cannot measure time. So therefore, time was not really measured, was not discussed. However, in the last 10 years, people, especially in optics, are now able to do what they call attosecond short pulses, which are very narrow. They are as narrow in space as a single wave length of the carrying wave. And therefore, this is now possible. And I was motivated to go into this subject just because of this attosecond and also because of other experiments. So I was actually introduced to this problem by Stephen Lage, who was here. He gave a lecture in Leszek's meeting, in which you have a pulse of radiation hitting a graph. The radiation can go many ways. And then you put here a detector and you measure what is the probability of detecting a certain time it takes of this pulse to pass a certain point here and reach the detector. And you get such a distribution. And my first question will be, is there a theory which explains this graph, especially asymptotically? And that will be the mathematical part. And my plan is, therefore, to speak, first of all, on the classical problem, and this is a random walk on a leaky network. I'll explain immediately. Then I will show why the scattering matrix comes in naturally into this game. I'll speak about scattering of short pulses, and therefore I can speak about transmission time. And then I speak about universality, what is the decay of this function if you are under some conditions, and then I'll show what is the effect on Anderson localization if I have time. So here it is. It is easier for me to say that. Imagine this is your pinball machine, but it's not really, it is a graph. So a particle can move on this, I didn't correct this. this is the particle it is supposed to be here. And it moves in a certain direction. And then it scatters whenever it reaches this space, this vertex. It can scatter with known probabilities to all directions, which all other neighbors which are available. And then if the probability is, if these matrices satisfy the requirement of conservation of probability, then the motion is completely regular. It does not, there is no leak. Then the probability to find the particle somewhere on the graph is constant, is 1. And if you denote this rho to be the probability to be at a certain directed edge, so moving in a certain direction on a certain edge, after n scatterings, then you find this simple multiplicative expression for the evolution of the distribution. You start with a certain distribution on the edges. You wait n times, and then you, after n times, this is the connection between the n times and n plus times. But the question is, how do you define now the sub-Markovian dynamic? And the story is the following. You pick up certain vertices, I call them h prime, and hj, and then you see all the lines, this lead should be connected at this point. And here comes the particle in this lead and feeds in, and then can go out from here, can go out from here, and if it goes out from here, you measure the time it took this particle to start here and to end up here. And this is the distribution that we are looking for. And you see that it is a leaky graph because the particle can be scattered backward, can be go here, and can go also somewhere else that you don't measure. And still, as long as the particle is inside the interior part of the graph, it behaves with certain probabilities. However, the probabilities do not sum to 1, because you can go out of the bounded graph, and therefore you can go out, and then you lose probability. And you ask, what is if you denote the set of paths which go from h prime to h after n times, then you can say that the probability to be at h, to go out from this this lead, having started at h prime, it is the probability to go from h prime to any of the adjacent edges, to propagate along the graph n times, and then to go out. This is just standard multiple scattering equation. And if you want to know in particular what is the length of time, time is actually length, it is distance. And if you call the distance of each edge, you call by L, then the probability to find a distance L, certain t, it is the probability that such sum of all these edges which are traversed until it goes out is equal to it, and then the probability to find this particular trajectory, and this is what we want. This is the probability to find the length, the delay t in a transition from h prime to h. So this is the, if you win, the pinball equation. That's just a diffusion equation or random walk equation for this particular problem. Now, the first aim that I have is to compute this equation, to find an estimate for this probability distribution. And this is what I did with my son and his friend Avner Kiro. And here we use the theorem which is called Wiener-Ikehara theorem. Are you familiar with it? Anybody heard about Wiener-Ikehara theorem? Marek?
Yes, I heard.
You heard? In what context?
I did.
In what context? You remember? So this was invented in number theory, for number theory, by I think by one of these gentlemen or both. Ikehara zeta function, is it the same Ikehara? Maybe.
Yes, this is the same Ikehara.
Maybe it's the same Ikehara. And he was interested, he was number theorist, and he used this theorem of theirs to provide a better or a shorter proof of the prime number theorem than the original French derivation. I forgot who was the inventor. So the theorem says the following. Suppose S of t is some integral, it is what we call in physics number counting function. It is a function which is positive for positive t. It doesn't decrease because it's count. Continues from the right because once you count one more, then you are continuing. That doesn't change, and then and such that the Laplace transform exists. So the Laplace transform with respect to the measure defined by this function when you take it as a derivative. So you look at this function. This is the derivative, and so this is a function of this is a function of z, the parameter in the Laplace transform. And you assume also that the transform exists for every z, so that its real value is larger than eta. Eta is a real parameter. And also, as you say, that if there exists a constant a, such that the difference between this function and the pole which occurs exactly at eta on the real axis, and they can continue the function analytically on the entire plane, then you can show that, and important also, that there is no other pole on the borderline x equals to eta, so x equals to eta is the only pole. Then you can show that this integrated measure behaves asymptotically as a e to the plus eta t, where a and eta are just given by the residue and the pole of this function. Okay? So you see, this is a very useful theorem for problems of counting. You count, you can prove that something happens to the Laplace transform, you compute the poles of the Laplace transform, you assume that it is a function which only has poles, you get the function, you can prove that it has only possibly poles and no other singularity. Then you look for the biggest pole on the real axis. It is unique if it is unique, so that there is no other pole with this real value, real z. Then you can guarantee that this is the behavior. So it's rather a strong theorem, and I don't know even if there are if this asymptotic, if it is known what are the correction terms. I think that nobody knows the systematic expansion, asymptotic expansion beyond the leading term. But the error can be estimated. Okay, so we would like to look at this function, which is the derivative of the s over there, the capital S. It is a function with a lot of delta functions. You take the Laplace transform. You play a little bit with this sum, and you can easily, by introducing this matrix, which is the probabilities multiplied by the corresponding e to the minus z LD, where LD is the length of the edge D, which appears on the left-hand side. You can easily show that this sum is nothing in the geometric series. You can write it in this way, and immediately you see that there are many poles. And the question is now to play and to show that this function satisfies the conditions which Mr. Ikehara and Wiener are requiring. And you can write it even in a more easy way, a more familiar way, by pulling out this determinant and using the adjugate expansion. And then you know what M is, they are positive, their sum is less than 1. So you have to study, the only poles are coming from here. This is the converging sum. I mean, this was the converging sum, so this is a finite expression. And you have to look for the zero set in the complex plane. And I shall not give you any of the details. I only quote some of the sketch of the proof. So what we have to do is to discuss the poles here. And you use the Frobenius-Perron theorem to show that there exists a certain x on the real axis, which is the maximum value, eigenvalue of m of x, and we denote it by lambda p. And you can also prove that the corresponding eigenvector of m of x is positive. And then you have 3 lemmas, and one lemma assumes also that the lengths which appear in this discussion are all incommensurate, so the lengths cannot be dependent rationally on each other. And this is necessary for the proof. And once you have all this and you prove these lemmas, you get the final expression which tells you that the probability to find a time t is equal to e to the minus t psi. Psi was the solution of the equation. Oops, sorry. Where was it? That this zero, this is the solution of this zero of this equation. So it relates to the matrix M, and so the connectivity and the length distribution appear in both in Xi and in the corresponding parameter, which we called before A. This was before eta, and this was before A. So this gives you the distribution. It is only valid if the graph is finite, because otherwise you cannot prove, you cannot use the Frobenius-Perron theorem. And it is proven only if the lengths are, as I said, not related rationally. So this is the result, exponential decay. It is universal. However, we are interested in waves, not in particles. And therefore you have to ask what is the Laplacian on the graph. And let me assume that you heard enough lectures. Can I assume that you heard enough lectures on graphs that you have heard about this before, or should I explain? What do you say? Adam, Mr. Chairman. Should I?
Just
briefly. Okay, so what do you do if you have a graph Laplacian? The graph has metric, so its length are given, and the Laplacian is the simple Laplacian on each of the edges. The length is given, and the connection between these solutions here and here are given by some boundary conditions which guarantee that the operator, the entire Laplacian, is self-adjoint. So you have a real spectrum. Now we don't have yet coupling to the continuum. So each point, on each edge, you assume such a solution, because this is free edge, then this is free propagating, counter-propagating waves. The boundary conditions can be expressed as scattering matrices, because you can think about this as waves coming and outgoing from each of the vertices, and then there is a connection between them. The connection is, the amplitudes are connected by these scattering matrices. And they are easy to compute for particular boundary conditions, the very simple expressions for this matrix element. And these sigmas are unitary for each of the vertices. And therefore, you can actually combine all the information that you have into a single matrix which has the dimension of all the directed bonds which are appearing on the graph. It is a unitary matrix. It contains the information about the lengths. It contains the information about the connectivity of the graph. It has the value, determinant of u is equal to 1 because of unitarity. And if you want to know what is the spectrum of the graph, it is enough to find the zeros of this secular equation, determinant of I minus u of k equal to 0. So those k which satisfy this equation are the spectrum of the graph. If the graph is indeed not connected to the outside world. Once you add connections to the outside world, as we did before, then you have now to couple this together. The solution on the interior edges will be the same as before. The solution in the outside will be also waves propagating either inside or outside. And then you have to couple them together. And the only difference between what we had before and now is that in each vertex where you added a lead which goes outside, you have to change the dimensionality of the number, which is of the degree, actually the degree of the vertex, because you added one lead going out, and therefore the sigma, which before 2 over d, where d is the number of the degree of a vertex, now it is degree plus 1. That's all. And if you make this connection, then the sum of sigma h squared may be less than 1. The matrix becomes non-unitary, subunitary, and that is the leaky part of the graph. You can define this evolution operator as I defined before by taking these probabilities, putting them into the sigmas and adding this phase factor. And then you can write the scattering matrix very simply like a multiple scattering problem. It is a multiple scattering also on the amplitudes, because you come in with an amplitude, you penetrate, you either penetrate or not, or scatter. If you come in, we have this multiple expansion, multiple scattering expression for remaining inside, and then you escape with this amplitude, and this is the definition of the scattering matrix. So this is the proof of the last statement. And then you can write this expression in a more transparent way. You say that, first of all, the probability to go from h prime to h, if the two of them are neighbors, then there is a certain b which connects them, and therefore there is a possible transition. Otherwise, you have to have some n scatterings inside until you go out to h. And then you can count all those, you can look at the group or the set of all paths which go from h prime to h, going through n edges. You can call this group A. Each of them has an amplitude which is the product of the w's which correspond to this transition, and you collect a phase on each of them, and the phase is the sum of all the lengths of edges which you have gone through, and this is the S matrix. Okay. And here are the expressions which I just mentioned before, and now the question is, what happens if you scatter a short pulse given the S matrix? Now, suppose that you scatter a wave packet which is defined by a certain envelope function. For example, this envelope function. You assume that it is also normalized in this particular fashion. And because we are dealing here with the wave equation, not with the Schrödinger equation, the dispersion relation is linear in k. The energy is proportional to k, not to k squared. So the wave packet is defined by the integral over all the possible k's with this wave, with this weight, this envelope function, and at each time you have the psi at k, and you have to integrate this. This is just coming out of the definition of time evolution in this particular problem. Now we know that we are sending in, let us say we are sending in a wave which is propagating inwards only through the lead h prime, and we want to know what happens in the lead h. This is the experiment that we want to do. And that's what we want to compute. So what happens is that you have to take the component of this business and to see what is the value of the wave function at the particular point where you put the detector as a function of S, given that S and T are related by this. That's simple, the standard definition in quantum mechanics, and out of this you get immediately that the probability distribution of S's are time delay, and suppose that you put the detector at distance 0, is just absolute value squared of this Fourier transform. Now, it is very nice to have the S matrix, because as you know, the S matrix is measuring the effect of the scatterer minus the motion in the free space. So it measures immediately the delay, because it subtracts everything which has to do in the evolution in the free space. Here in the graph it comes out automatically, but it's correct for every system. And this is a very nice way of writing it. You can also write it as a this absolute squared is what they call power spectrum, right? But any power spectrum can be written as the Fourier transform of a autocorrelation function. Now here the autocorrelations are between the S's. This one is computed xc, the mean value, plus eta over 2, xc, the mean value, eta minus eta over 2. The integration over the xc parameter is not going on the entire space, but it has to go over what is determined by the content, the frequency content or the bandwidth of W of omega of k. And the Fourier transform is also restricted to a certain domain because of the fact that this is not free to change altogether. So this is the formula which is the basis for our discussion. And you can now plant this expression which we wrote before for the S matrix into this expression, and you get such a beautiful expression. What it is this you always count trajectories, how many times the trajectory, how many edges the trajectory was going through. Alpha and beta belong to the set of paths which go from h prime to h in the time n, and this is the result which you get if you plant the distribution, the Gaussian wave packet envelope which I had before in this way. Now notice that this expression here in sigma becomes a delta function, and this becomes a Kronecker delta function when I go to the limit that sigma is much smaller than k0, somewhere appearing, and therefore I can write this in this form, which can be easily understood. You have a sum over all the possible lengths, integers. The length of a trajectory can always be written as an integer times L. L is the length of a certain edge. Q is the number of times that this trajectory was going. Qm is the number of times the trajectory went through the edge M. So this is what appears here. And then you sum over all the possible Qn's. If you assume that the L's are independent rationally, then this number depends only on the Q's, and you cannot get two lengths which are different if the Q's are not different. So for now, 10 minutes, okay. So I don't want to give you details, but I want just to tell you that there is a very simple systems for which you can carry both the classical computation and the quantum mechanical computation exactly. And this system corresponds to, I don't know, maybe you don't see it, but you can think of this as a graph. This is just an axis so that it helps you to see what you see over there. The red ones are so there is a graph at each line corresponds to a vertex. This is the edge, so it is a linear graph. You can think of it as a chain of unequal beads. Each bead is a scattering matrix, scattering center. So, and it goes to half, so the half line starting at 0, going to infinity, is full of these beads. And then the trajectory starts here from the left, continues chuck. Here it returns this way, and then goes back to here, and then goes back to here. The point is that the number of going right and left must be equal, because you finally want to go out from this point, and therefore the black parts can be removed, which helps to count. This is another example of the same problem, but again, a different topology. You see that the number of M1, M2, M3, M4, the number of red arrows is constant, but the topology is different. So you have to count all these businesses. So there are many isometric but geometrically distinct trajectory, and it's very difficult to count them. Now, counting the trajectories in this particular problem can be done. And why? Because, first of all, the sum of all the m's must be equal to our parameter n, the number of edges which you transverse. So the number of families of equi-length trajectories is the number of times you can partition n into a sum of m's. This is a problem in which you can solve. And then at each vertex, you have the number m1, and you ask yourself how many arrows you can arrange along between that will correspond to a topologically different ordering of the arrows on the right with respect to the arrows of the left, on the left, where the ordering is with respect to the construction that every endpoint has to be thought as connected by black arrows to the most left one. So this is connected to this. This is connected to itself, it continues, and so on. And you have to remember that the topological time, this is what we called previously n, is equal to twice the number of m's. And the metric time is just this particular business. So this can be done. In particular, you have to also to introduce the S matrices, and you can write easily the element of the S matrix which you are interested in, scattering from here and going back to here. It depends on the product of these parameters. You see that there are i's anywhere, sinuses, cosinus, they have different signs. And then you can compute these things, and without giving you too many details, it's hot and tiring, you can do the calculation after averaging over the angles, over all the S matrices possible. And then you can prove that you can show that if you do the calculation classically, namely you add up probabilities, or if you do it quantum mechanically, you get different answers. This can be done, as I said, by the work which I did once with Holger Schanz, and you can show that in the classical limit you have t to the minus 3 halves. Now you remember that if you have one-dimensional diffusion problem, the probability to return to where you started is 1 over t to the half. Here you want also to know the rate of the change, because you have the time of the evolution. You have to derivate with respect to the time. 1 over t to the half, take derivative, it is 1 over 3 halves. To do the calculation, you can also do it explicitly without this hand-waving argument, and you get to the minus 3 halves. Now here, one knows for sure that the problem is Anderson localized on the whole line. What do you guess will be the topological, so the quantum mechanical distribution? How will it depend on t?
I remember.
Sorry?
I remember.
You remember what you heard in my lecture, but those of you Well, there is Anderson localization. So you see, usually Anderson localization has to do with exponential. So do you think that this will be exponential here? No. You can prove that it's t to the minus 2. So you see that the existence of Anderson localization changes the power law of the decay of this distribution. And this is a nice result. Mathematicians don't know about it, didn't know about it. And why? Because nobody was interested in the time domain. Everybody was interested in the spectral properties, which are solutions of the time-independent problem, and nobody bothered to look at it in the time domain. If you look at the time domain, you have a new characterization of Anderson localization relative to the corresponding classical model, which is nice. Was not known to the mathematicians. At least two mathematicians whom I asked didn't know about it. One of them is Barry Simon, one of the mathematicians who worked a lot about Anderson localization. The other one is Michael Weizmann, who also worked a lot about Anderson localization, and they didn't know about it, and it was a surprise for them. So I think it is an interesting problem to work on. Right, Kasha? Good. And then you can do numerics, and the numerics, of course, proves what otherwise I will not show you. So the numerics works, and never mind the details, but the last line is that it works not only under our conditions, but in general. And I can only summarize by some open questions and to be done. We did not really look at the distribution of metric delay lines, the delay times. We did not look at the dimensionality. We looked at one dimension. We can also ask the question in many dimensions. You have scattering from the half space. You define a scattering problem on a graph or on a lattice of some kind. We didn't calculate the role of dissipation. You can always, if you want to compare with experiment, then you have to compute the dissipation. What does it do? Usually it is a problem. What we did here under the carpet, we didn't look at it, we didn't say it, but it is really lurking under everything which we did, is that we do not speak about Anderson localization as a problem in spectral theory, but in, if you wish, in scattering theory, where you don't speak about energies, real energies, but you speak about resonances. So nobody before spoke about this problem of Anderson localization as a problem of resonances. And then you can also, when you want to limit yourself to graphs, you can ask, for example, what happens if you scatter not from a line, but from a tree. And then everything can go. It's a very complicated problem, but this is something which is on our list. And nothing remains for me to do but to thank you for your attention.
I have a remark rather than a question. Back in the 70s of last century, there was a very popular problem going under a similar name, namely people were interested in the delay time statistics of the pulses created in the superfluorescence. Actually it's a situation of starting from unstable point and then going to self-acceleration. Yes? And the quantum fluctuations of the initial state are really are enhanced in the process. Mm-hmm. That has been done, the theory for that has been done very nicely by Fritz Haacke and Roy Glauber. I wonder whether there is some relation to your work or not.
I wonder also, and thank you very much for the remark. And since I know Fritz Haacke very well, I shall easily remember his name. And
you must know Roy Glauber as well.
No, he is older, and I never worked in his. I mean, he did a lot of things. So I didn't know him personally. I met him maybe once or twice, but I don't remember. We didn't have any relation, like I had with Fritz for sure. The only point I think that is different in this respect is that we enhance the here in scattering problem when you have pulses. You have to know how to introduce the wave packet characteristic. It is very important in analysis. If you start with a decaying of a single state, then you have to make some assumption about how you start and how. So this is a slightly different, maybe different. Maybe certainly it is related. But you're 100% right. I should look at it, and I shall see whether it is.
Their solution was also very elegant. They were able to relate it to some functional integral that they were able to compute at the end.
That is not very far away from here, because you can write also the S matrix as a functional integral, and it is a functional integral in momentum with boundary conditions on the momentum rather than the points. And this can be done. As a matter of fact, this is done in the semi-classical approximation. So it's a very nice remark. Thank you very much. I don't know.
Are there any simple, exactly soluble models, like, for example, the collection of wells in one-dimensional quantum mechanics?
Well, this is, you see, the graph is synonymous to a collection of wells, because what is a graph? A graph is free propagation and S matrix. Free propagation, S matrix. So
know the dynamics of the single well, then
yeah. And then on my plan, I'm planning, when I finish the writing, this is not yet written. I'm writing now the paper, but when I finish this very boring job of writing a paper, to go into the Anderson model, which is discrete model, in which you have, you remember, you have this discrete transitions and the variation or random on-site potentials or random energies. And this can be converted into a similar graph, but with interesting differences, because, for example, in the Anderson model, you are dealing with a band. The spectrum is not infinite, it's in a band. So there are interesting problems how this will evolve, and how, but this is possible. Everything which can be expressed as an independent scattering over succession of intervals coupled unitarily is of the same genre. I don't say it's exactly the same, but it's of the same genre. So I believe this can be done. But if you ask me what happens with trees, I am not sure it can be done. At least not analytically. Yes, Leszek.
So when you look at the analogous experiments, you have this really short paths,
Yes.
coming paths, and then quite complicated outgoing paths.
Yes.
You are interested in this very, very long path.
Yes.
But you have some intermediate structures. Would you link this intermediate structure, this outgoing paths, with some internal structure of the graph?
Yes, if you have I think that to do numerical, what you suggest is to essentially, I cannot do it analytically, but to do it numerically, I think it is possible if you know how to deal with oscillatory integrals. And if you can do that, then it is possible to do it. And probably I didn't try, Holger Schanz is now trying to do it, but I think it is doable because the S matrix is only 6 by 6. You can write it analytically, so it's not not 6 by depending on how many connections you have. But the internal dynamics is simple. So I think it can be done numerically at least. So, dziękuję bardzo.